Good morning, children. Today we will discuss about line coding or PAM formats. Let us go with the presentation. Let us discuss about line coding or PAM formats. So what PAM abbreviated pulse amplitude modulation, pulse amplitude modulation formats. So what is line coding and why it is used? Suppose if you consider any binary signal or discrete signal, if you want to transmit over a band limited channel, then the signal because of overlapping of adjacent pulses. Because of overlapping of adjacent pulses, whenever we are going to transmit this binary signal or discrete signal over a band limited channel, it will get dispersed, or we can say it is distortion. So this type of distortion or dispersion is known as intersymbol interference, ISI. So therefore, instead of transmitting the discrete signal as it is on the transmitting medium, here we have to first convert this signal, binary signal or discrete signal, into a PAM suitable format. So whenever we want to transmit the binary signal or discrete signal over this band limited channel as it is, first we have to transmit, here we have to first convert this signal into a PAM suitable format, and after this it is transmitted over the channel. So here let us see the different kinds of PAM formats which are used. So the PAM formats used are known as line codes. So the different kinds of PAM formats used are known as line codes, and let us see the different types of PAM formats here. Line codes or PAM formats. So here let us consider the first one, unipolar. Unipolar, in the name itself we have, uni means single pole. That means we don't have any negative pole in the case of unipolar. And here in this one we have two, again we can see here two types here, RZ, NRZ, unipolar RZ, unipolar NRZ. So here RZ represents the return to zero, RZ represents the return to zero, and NRZ not return to zero. NRZ not return to zero. So here this is a unipolar signal, so that we have only a single point. So we have only a single point, single pole we have. So let us see. Here this is the time axis. So here this is the time axis, and here along this we have the amplitude, and here this is the amplitude which is here constant, and here this is 0, and TB here from here to here. We have the time period of the binary symbol. Here we are using the binary symbols zeros and ones. So here TB, it is the B, suffix B represents the binary. So T represents time period of the binary symbol from here to here. So full, this one. This is total time period of the binary symbol. And if you consider at half, TB by 2, T suffix B by 2, half time period. So here we have considered the signals, binary signals here, 1, 0, 1, 1, 0, 0, 1. So binary here data we have 1, 0, 1, 1, 0, 0, 1. So in the name itself we have unipolar return to 0, unipolar not return to 0. First let us see the unipolar return to 0. So here we have the symbol 1. So here from A, it will start from A, and at half time period, so at half time period, it automatically returns to 0. That means here we can see. So it starts, the signal here, it starts, the pulse starts from A. So A means here at here, A, once here we are using here 1. So from here to here, so it returned to 0. So at half time period, this return automatically, this pulse returns to 0. Again we have 0 here. So again the pulse, it moves on 0, because here this is a 0, pulse moves to 0, and again we have 1. So again we can observe at A. So pulse raises up to this mark A. And again this pulse returns to, at half time period, again it returns to 0. Again we have 1 after 1 we have side by side we have 1. So 1 is followed here 1. So at 1 at half time period, TB by 2, again it returns to 0, and again it increases to A. here we can see the pulse. Again, it goes to this amplitude. So A. Again, here we have 2 zeros. So the pulse returns to 0, and here again 0. So it goes on, and again it goes on, and again here we have. So again we have it goes to the A value here. So here A 1. Again it returns to 0. So here this is the unipolar return to 0. That's why we don't have any. Here we have only positive sign. We don't have any negative sign. That's why here we have the values above the 0. We don't have any values below the 0 here. Now let us consider this unipolar non-return to 0. So again here also we don't have any negative signs, negative signals we don't have here. So let us consider here. Again here we will consider the binary data 10110001, and let us see again here it not returns to 0. See, let us see the difference between return to 0 and non-return to 0. So the pulse here started at A because of 1. This started from A, and at half time period, it is not written to 0. It goes on. It continues here, and 0 is there. So because of 0, it goes 0, and again we have 1, 1, 1 following 1 here, 1 followed 1. So again we will have the value 1 at A. Again it not returns to 0. Again it goes on. Again we have 1. Again the pulse moves. Again here we have 2 zeros, so the pulse moves to 0, 0. Again we have 1, so again the pulse moves at A. So this is the difference between unipolar RZ and non-RZ and unipolar NRZ. So here this is the main difference. In the case of this returns to 0 at particular half time period, it automatically returns to 0. But in the case of non pulse, it does not moves, it does not returns to 0 at half time period. So this is the main difference. And if you observe here, if you compare width of RZ and NRZ, the width is more in NRZ when compared with the RZ. That means here NRZ pulse width is more. Therefore, energy of the pulse is more. All are in the above 0. There is no negative part here. So since we don't have any negative part, so here we see no separation between the pulses. Therefore, the receiver needs the synchronization, because here we don't have any 0 here. Negative, we don't have any zeros. Negative sign, we don't have any. So that here we have to see. No, we are not seeing any separation so between these pulses. Therefore, so here this is the transmitting. We are transmitting like this. That means whenever the receiver needs to receive these pulses, here we need some synchronization. So to detect the unipolar non-return 0 pulses. Why we need the synchronization? Because the data which we are transmitting should be equal to the receiver data also, so that the synchronization is necessary to detect the unipolar NRZ pulses. So we need synchronization. So here we need the synchronization. So if we compare these two formats, RZ and NRZ, so then you will see NRZ pulses with this more when compared with the RZ pulses. So hence these are unipolar formats, single polar. We don't have any bipolar. So these are the unipolar formats which have average DC value. So if we have DC value 0, so if you want DC value 0, here we need the negative values also. But here, because of unipolar format, we don't have any negative sign. Negative we don't have. So here average DC value, we can observe the DC value does not have a value. It is average DC value is there. So here DC value not equals to 0 here, because we don't have any negative symbols below this 0. So here we have average value, DC value. So DC value does not have any information. So all the above x-axis only. So there is no negative part here. So it has some DC part. Now let us, here we have discussed about unipolar RZ and unipolar NRZ. Now let us discuss with the polar. Polar means here we have two poles here, positive and negative. So let us discuss about polar RZ and polar NRZ. Let us see this figure. So here already we have seen the unipolar, we have only positive values, but here it is polar, we have positive and negative values. So polar means having two poles here, positive and negative, both the parts we have. So hence we have positive part is there and negative part is below this positive part. So whenever we have positive values and negative values, so we have DC value is becomes less or 0. When these get cancelled, that means here what will happen, we don't have any DC value. DC value will becomes minimized. So here we have DC value is less. So if we consider in RZ, that means return to 0. So here this is a by 2 we have considered, and here in the center time axis it is 0, and here below this 0 or below this positive part we have minus a by 2. So both part we have. So it is RZ, it returns to 0. First let us consider RZ, next we will go for the non-return to 0. So let us see, here this is the RZ which returns to 0 after the half time interval. So here if we can, here the data it is binary sequence 1 0 1 1 0 0 1. So here we have it returns to 0. So at TB by 2 at the half interval it automatically returns from this part to 0. Next we have 0. So here 0 means we will see here in this below this axis 0, here below this axis 0, and again we have 1. So again we will it takes the pulse from here a by 2 to again it returns to 0. Again we have another pulse, again we have the here from a by 2, here we have taken, again we have two zeros, again the pulse returns to 0, and for two zeros we have the below the negative axis below minus a by 2 we will see here, and again we have positive, again the pulse goes to if we consider the polar return to 0, we can see the zeros in the negative side. Below this 0, we will this is the polar returns to 0 and non returns to 0. So here if you consider here the pulse non returns to 0, let us see. Here we will consider the same binary values 1 0 1 1 0 0 1. So here the pulse starts from this 1 because of 1. So here it is from a by 2, and it does not returns to 0. It is not going to 0. It is not written in the negative side, negative value. It takes 0 in the negative values, negative minus a by 2. So 0, again we have two ones. So the pulse goes again from the positive a by 2, and it is not returning to 0. Again we have another one. So it continues, the pulse continuing, and here here we have two zeros. Again the pulse returns to 0, and it comes to the here two zeros. Again the pulse in the negative a by 2, negative side, and again here we have one. Again here the value the pulse moves from at this particular point. So here this is the time axis. So so here we can see the time period of a binary sequence here total here. So because in NRZ the width is more when compared with the RZ. So polar RZ and polar NRZ. So here because of these negative values we have if we have the positive values equals to the negative values, the DC value becomes 0 minimum. So here we don't, so DC value it is minimum, very less in the case of polar RZ and polar NRZ. Suppose if they are in equal number, that means number of ones is equals to number of zeros. 1, 2, 3, 4, 1, 2, 3. But here we have only 3 zeros and we have 4 ones. But if we have 4 ones and 4 zeros, the value becomes, DC value becomes 0 because the positives and negatives get cancelled here. So here in this polar RZ and NRZ, we have DC value, it is minimum DC value. And let us discuss about bipolar. Bipolar NRZ. Let us discuss about bipolar NRZ. So here, let us see the figure. So bipolar NRZ, or we can say we have an alternate name for this bipolar NRZ, alternative mark inversion, alternative mark inversion. So see, let us see. So bipolar NRZ, or we can say alternative mark inversion, or it is abbreviated AMI. So if you consider the bipolar NRZ, or if you consider alternative mark inversion, so let us see. So here the binary sequence 1 0 1 1 0 0 1, and here this is the time axis, and here we have a 0, and we have bipolar. So we have positive values and negative values, and here non-returning to 0. Here we are discussing bipolar non-returning to 0. That means we don't have the pulse, it does not returns to 0. So let us see it here. 1, it is not written to half time period, it moves up to full 1, and here we have 0, so that it goes to 0, and next we have 1. So alternate, so it focus only on ones. Bipolar NRZ or alternative mark inversion, it focuses only on one value 1. So already we have 1, so it is positive, and if you have here another 1, so it takes the value negative value, negative. So here here in this case 0 is here this line, and 1 after another 1, if we got another 1, it takes a negative a value. So negative, and it is not returning to 0, it goes on, the pulse moves like this, and again we have another 1, so this one is followed this one, so it takes positive. So one positive, negative, positive, negative, like that it takes. That means alternative mark inversion, the name itself we have. So for this one again it is on above positive value, again for zeros, 2 zeros, so it moves on this time axis, and again 1. So already we have this positive 1, positive a value. So the next alternative one, it takes the negative. That means it concentrates only on ones. It does not matter how many zeros we have. It matters only how many ones we have. So that means here it is alternate mark inversion. So it keeps on changing for successive ones. It keeps on changing for successive ones. So if you have even number of ones, then the DC component of the waveform would be 0. So 1. If we have even number of ones, so the DC component value of the waveform would be 0, because the positive and negatives get cancelled. So here for 2 ones we have plus a amplitudes, and for another 2 ones we have minus a amplitudes. That means DC component will become 0 here. Now let us discuss another one. So already we have discussed about bipolar NRZ or alternative mark inversion AMI. Now we will discuss about split phase Manchester. Split phase Manchester. So here if you consider in the case of split phase Manchester, here we use 2 kinds of pulses. Here we will use 2 kinds of pulses. That means here the 2 kinds of waveforms here we will use. If I want to transmit one, then it will here let us see here. So if I want to transmit 1, the symbol here we will use this one, and if I want to transmit 0, the symbol is like this. That means here what is the difference between these 2 signals, these 2 symbols? Let us see. So if I want to transmit 1, then the positive half interval pulse. So this is the positive half interval pulse, which is followed by the negative half interval pulse. Here this is negative half interval pulse. So positive half interval pulse is followed by the negative half interval pulse. then the transmitting 0. So if you see this negative half interval pulse, this is the negative half interval pulse. So which will be the negative half interval pulse will be followed by the positive half interval. So for 1 I will use, so here let us consider the data 1 0 1 1 0 0 1. So here for 1 I will use this symbol, and for 0 I will use this symbol. Like 0 average DC value is 0. So irrespective of ones and zeros, we have always 0 average DC value. So in this mode, power saving is very high. In this mode, power saving is very high.